Cell cycle regulation is important. Without cues to grow or to stop growing, cells would either multiply non-stop, forming masses, or they would never multiply. There are three major checkpoints in the cell cycle: at the end of G1, end of G2, and during metaphase. Progression through checkpoints is mediated by cyclins, CDKs, and tumor suppressors. Cyclins are proteins that bind cyclin-dependent kinases, or CDKs, activating them. CDKs are enzymes, specifically kinases, meaning that they phosphorylate proteins to activate or deactivate them. Different combinations of cyclins and CDKs promote different actions at different points in the cell cycle, signaling starts or stops. By having complexes critical to cell cycle progression, there is a way for the cell to shut off the progression by inhibiting those molecules. For example, CDKs are indirectly regulated by tumor suppressor protein p53. p53 can activate several pathways, including cell cycle arrest when there is DNA damage. I will go into the details of this mechanism in another video, but in this video, we will look at the functions of cyclins and CDKs throughout the cell cycle. If we unroll the cell cycle to form a graph with time on the x-axis and concentration of cyclins on the y-axis, we can see the amounts of different cyclins present at different points in the cycle, showing which cyclins are needed when. A cell can switch from G0, or cell cycle arrest, to G1 once cells have achieved a critical size. For multicellular organisms, growth factors and mitogens, which are substances encouraging cell division, need to be present. For unicellular organisms, nutrients must be adequate in surroundings. Once G1 is initiated, cyclin D is synthesized and drives the G1 S phase transition. In eukaryotes, cyclin D binds with CDK4 and CDK6. These two complexes can partially phosphorylate retinoblastoma tumor suppressor protein, or RB for short. RB is bound to E2F, a transcription factor. When the cyclin D CDK4 and cyclin D CDK6 complexes partially phosphorylate RB, it loosens its grip on E2F. E2F can then activate transcription of the cyclin E gene. Cyclin E binds CDK2, and this complex fully phosphorylates RB, completing its inactivation. Cyclin E also phosphorylates P27-KIP1, an inhibitor of cyclin D. Phosphorylation of P27-KIP1